Welcome to this video on navigating boundaries through the mathematics of linear constraints and inequalities. We'll explore how these tools help us define ranges of possibility. Equations demand exactness, but reality is often more flexible. When we can't map to an exact point, we must map a safe zone using inequalities, as shown in this budget example. Inequalities come in many forms, ranging from simple numerical comparisons to strict or slack boundaries that define whether a range is inclusive or exclusive. When manipulating inequalities to isolate a variable, remember that adding or subtracting doesn't change the boundary. However, multiplying or dividing by a negative number is a different story. This is the golden rule, or negative flip. Because multiplying or dividing by a negative number reflects values across zero, the directional boundary must also flip to maintain mathematical truth. Visualizing these limits is key. Strict boundaries use open circles, while slack boundaries use solid, inclusive circles. The syntax of your inequality dictates the architecture of your graph. The environment dictates the solution. Whether you are working with natural numbers, integers, or real numbers, your boundary is only as useful as the numbers permitted within it. Let's walk through mapping a solution. By isolating the variable through standard algebraic steps, we can clearly visualize the resulting solution set on a number line. In this real-world application, we calculate the minimum exam score required to maintain a specific average. By solving the inequality, we find the exact boundary for success. Sometimes we deal with overlapping constraints. By defining multiple inequalities, we can narrow down a set of valid pairs that satisfy all conditions simultaneously. Inequalities are vital for managing chemical tolerances. Here, we model concentration levels to ensure a mixture stays within a safe, effective range. When we look at a system of inequalities, we are seeking the intersection, a specific zone where multiple constraints are true at the same time. By visualizing these systems, we can see the overlap clearly. The intersection of these truth zones defines our final, valid solution range. Finally, we apply these concepts to operating ranges. By converting temperature scales, we can determine the safe operating environment in Fahrenheit. To conclude, linear inequalities are more than just alternative equations. They provide a fundamental language for defining the boundaries of possibility in our world.